What are atoms? How do they look like? Let's take a look into what we have learned about them and how we think of them. The history of the atom. Part 2. This is a pool ball. A rigid sphere, to good approximation. It can move and it can interact with other rigid spheres and rigid walls by collision. This is not what atoms really look like, but people thought so for a while. Dalton and the chemistry of gases. Now, this will be a story of two fields of science working on very much the same questions, but from different perspectives, and also cross-fertilizing each other in the process. So, not like this, but more like that. First, we will talk about chemistry, the chemistry of gases. In ancient and medieval times, there was only this practice called alchemy, and it concerned itself pretty much with finding a cure for all illness or turning tin into gold, both with, let's say, moderate success. But people did learn some legit things along the way. In the 17th century, people began to apply the scientific method to alchemy to separate the useful stuff, the actually useful stuff, from the hocus pocus. A good example of this is Robert Boyle's The Skeptical Chemist from 1661, and all of these efforts would then go on to create the field of chemistry. Initially, a lot of focus was given to gases, of measuring the properties like pressure, temperature, volume, and trying to figure out their behavior. In turn, this led to the laws of Boyle, Charles, and Gay-Lussac. Joseph Proust managed to deduce the law of definite properties. And it says that for simple compounds, the ratio of the masses is equal to the ratio of the atomic weights of the elements. For example, to create carbon monoxide, you need 3 parts of carbon, 4 parts of oxygen. So the same ratio of 3 to 4 must also apply to the atomic weights of carbon and oxygen. But there can also be different compounds of the same elements. For example, you can have carbon monoxide and carbon dioxide, etc., etc. And this case was explained by John Dalton and his law of multiple proportions. And it just states that the ratio of the masses will always be small whole numbers. For example, as we already said, CO has 3 to 4, CO2 has 3 to 8, and so on and so on. A few years later, John Dalton was able to explain all these findings using his atomic model, which he published in his work, A New System of Chemical Philosophy. All chemical elements are made up of atoms. Chemical reactions are rearrangements of atoms. Atoms of different elements combine in simple ratios to form chemical compounds. All atoms of the same element have the same mass, the atomic weight, same size and proportions. Atoms are indivisible and can't be created or destroyed. Maxwell, Boltzmann, and the kinetic theory of gases. At around the same time, ever more physicists came to support the idea that heat was not actually a substance, but a form of motion. Which of course begged the question, motion of what exactly? The Swiss physicist Daniel Bernoulli, in his work Hydrodynamica, already described gas as consisting of tiny particles and used this to explain pressure or other properties. Atoms were modeled as perfect hard spheres that collide perfectly elastically with other atoms and the walls. In this picture, pressure is just a statistical effect caused by a large number of these collisions with the walls. And this has many consequences that you can actually measure. For example, a higher density of the particles means that you get more collisions with the walls and therefore a higher pressure. Or a higher temperature of the particles means they have a higher average energy, so you get more forceful collisions and therefore also more pressure. And this so-called kinetic theory of gases was then further refined in the second half of the 19th century mostly by contributions from Clausius, Kelvin, Maxwell and Boltzmann. Maxwell derived the statistical distribution of velocities that a gas would have to have if it consisted of atoms. Already in the 1860s and in the 1870s, Ludwig Boltzmann improved on that. And this theory allowed physicists to describe the behavior of gases and also to calculate numerical values for pressure, for temperature, or for specific heats of gases. And the great thing with this new theory is you can take a new phenomenon, heat and temperature and pressure and gases, and completely explain it by using something that's already very well known. Motion, simple motion. And the only thing necessary to explain all of this is to assume that everything is made up of tiny particles we can't see. Atoms. Dalton's model. Significance and legacy. So, how well does Dalton's model hold up with what we know today about atoms? All chemical elements are made up of atoms. Chemical reactions are rearrangements of atoms. Yes. Atoms of different elements combine in simple ratios to form chemical compounds. Mostly true with rare exceptions. All atoms of the same element have the same mass, the atomic weight, same size and proportions. Mostly true, but we did find there are different variants of the same element that show the same chemical behavior but different mass. These are called isotopes. And technically, ions also slightly differ in mass. Atoms are indivisible and can't be created or destroyed. With the means of 1808, that was correct. But since we have learned how to split atoms, and we have also learned that it's possible to convert mass to energy and the other way around. So we can destroy or create particles, if we have enough energy to do so. Why was the model abandoned? Mainly because we found out that atoms aren't just rigid spheres, but they actually have an inner structure, they have components. And with these advanced models we could explain even more. And also atoms have a connection to electricity and electromagnetism, and this is completely missing here. But even with its known shortcomings, the model still has its uses. It's still educational and it still can explain a lot of simple mechanical properties. Finally, despite all the successful predictions of the model, atoms were still being doubted by the end of the 19th century. At the time, it was seen as a useful model. But just that, a model. The actual reality of atoms was still not taken serious by most.